Good afternoon. Excellent. So the last time we talked about weak acids, and weak acids are different than strong acids. Strong acids totally dissociate into HVO plus the anion when you put them in water. And this has a very large K. Strong acids have a very large K, and they are completely dissociated, so the equilibrium is with the product, very much so. Weak acids don't dissociate completely, so that means there are reactants left on the left side, and with this your K is smaller than 1. That's the difference between a weak acid and a strong acid. K is the first thing. And if you have a weak acid, it reacts with water just like a strong acid does. It reacts with water, and water is a base, to form the conjugate acid, and the acid becomes its conjugate base. So this is acetic acid, for example, becomes its conjugate base, and that's AC minus, the acetate ion. So the equilibrium constant for this is 1.8 times 10 to minus 5. It's smaller than 1, a lot smaller than 1. So this is a very weak acid, and with this your pKa, that's the logarithm of that number here. That's minus 4.7, and you multiply with minus 1. That's our convention that we have to get from K to pK, and with this the pKa is 4.7. Now the next step is very different for weak acids compared to strong acids. So you have this acetate ion, that's a base here, and that base, of course it's not a very good base, reacts with the water to form undissociated acetic acid, HAC, plus OH minus. And for this we can now formulate a base constant, because this is a base here, and so that's the concentration of this times the concentration of this divided by the concentration of the free acetate ion. And this is 5.6 times 10 to minus 10. So it's a lousy base, okay? But it is a base. And with this you can calculate a pKb. You take the logarithm, multiply it of this here, multiply it with minus 1, so you get pKb of 9.3. And then you have seen this is a conjugate acid-base pair here. So you see the acidity constant is given by this equation here, and the base constant is given by this equation here, which is the same than this here. Okay? So if you multiply the acidity constant with the base constant of a conjugate acid-base pair, then you get what? So let's do that here. So these HAC is in the denominator here, and it's in the numerator here. That cancels. Then the AC is in the numerator here, and denominator here. That cancels. So we have then Ka times Kb is HVO plus times OH minus concentration. And we all know what this is. This is the equilibrium constant for water at that temperature. Okay? So you can say this here is true. The same, of course, you can do the same thing then for a weak acid, a weak base, and its conjugate acid. The conjugate acid would be NH4 plus. There's the plus, it sits right here, it's a little bit shifted. NH4 plus reacts with water. Water is a base, so it takes this, forms H3O plus, its conjugate acid, and the acid becomes its conjugate base, NH3. Okay? So what does that mean? So it produces here some extra H3O plus ion, gets more acidic, a little bit more acidic, and this one got a little bit more basic than compared to a strong acid or base, because it dissociates completely in its components, and that's it then, nothing happens. But here with weak acids and weak bases, there's a second step involved, and we get to this today a little bit later. So when I left you the last time here, we had this question. We have two acids, HA1 and HA2, and we know that the pK of A1 is smaller than the pK of HA2. And so now you have that equilibrium, the acid 1 plus the ion of acid 2, the anion of acid 2 gives acid 2 plus the anion of acid 1. So that's obviously the stronger acid will win. And I'm asking you, is the K smaller than 1, equal to 1, or larger than 1 for this equilibrium here? Why don't, and you had plenty of time to think over this over the weekend, and you didn't think about nothing else. You only thought about this problem, okay? So I know that. That's why you're going to be able to answer this now with no problems whatsoever. So which one is true? Is the equilibrium on this side? Is the equilibrium on this side? Is K smaller than 1? Is K larger than 1? Or is it exactly 1? So this is what we had done at the beginning, or at the end of the last lecture. And many of you had voted. I think everyone has voted because you get credit for it. By the way, today, a year ago, it was over 90 degrees. I remember that when I gave that lecture. So there's two things you need to know. What pKa means, and if you compare two pKa's with each other, how does this precipitate is the wrong word, how does this work out for the Ka's? Okay, which one is the stronger acid? So it's the competition of the stronger acid, of the competition of the acids, and as in life, the stronger one always wins. Okay. So many of you said, or didn't say, that K equals 1. I agree with you, okay? But now you have to think about an answer. Is K smaller than 1 or larger than 1? So if HA would be a stronger acid than HA2, okay, then the equilibrium would go to the right here, okay? This would be winning then. HA1 would be winning. And with this, what would be, if the equilibrium would be here, so this would be larger and this would be smaller, so K would be larger than 1, okay? If HA would be the weaker one, HA1 would be the weaker one, so this one would go over here, then HA2 would be the stronger one. And with this, you have this divided by that, the products of those concentrations, and this would make K smaller than 1. So what is it? Think about your pKs and your Ks. I give you 1 minute for it. I got to get moving here. Where's Richard? Not here. Which is the stronger acid? 1 or 2? Okay, then you have the answer. But you didn't hear what he said. Okay, I go with C. Now, why is that? pKa1 is smaller than pKa2. What does this mean for the K? K1 is larger. Ka1 is larger than Ka2. And if this is larger, then it pushes the equilibrium to here. Okay? And with this is the answer. pKa1 is smaller than pKa2, and you how to deal with pKs and Ks. So Ka1 is the stronger acid, and with this it pushes it to the right. That means there's more of this here in concentration and less of this, so this is larger than 1. Okay. Alrighty. Now let's do another one. We have, again, this darn acid 1 and acid 2, and we have pKa1 is smaller than pKa2, the same what we just had here. Now I have this equilibrium here. What is the K for this equilibrium? Is it A, Ka1 plus Ka2 is K, or K is Ka1 times Ka2, or C, K is Ka1 divided by Ka2? Why don't you think about this and give me your answer, please? Why don't you? Huh? What I would do, I would write both equilibria and then manipulate one of them, and then I would add it up to get that equation. Okay, there's no real distribution. The only one is it's a linear distribution. So the C's have the majority. So as I said to you, I would formulate both acid equilibria, and then I would switch one, and then we'll add it together, and with this you would see what the answer is. Why don't you do that? Discuss it with each other. So this reacts with water to form HVO plus A minus, okay? And this reacts with water to form HVO plus A2 minus. This one is K1 and the other one is K2. One thing you need to know, of course, if you have to add K's or multiply them to get the overall K. That's the question. Yes, we're getting there. It's still linear, but steeper now. Okay, I go with the, I think we take C, okay? I don't think so, I know actually. So what you do is you say Ka1 is that equilibrium. Ha1 plus water gives H3O plus A minus. Nothing wrong with that, isn't there? So you do the same thing for A2. Ha2 plus H2O gives H3O plus A2 minus. Okay, so that's Ka2. But we don't want this. The equation was written differently. We had A2 on this side here. If you look at this, it's the equation A2 was in this side. So we got to get A2 somehow over here. So why don't we multiply this with -1 and we switch the equation? We do this here. Now it's over here. A little bit too many arrows here. But this needs to, what do we do with this here when we switch that? It becomes the reciprocal, okay? 1 over Ka2, all right? So now, forget these arrows. If we subtract the arrows, we're not going to be okay, all right? So this is Ha1, okay, plus A2 minus, and this one here cancels against this one, and this one cancels against this one, so it's Ha1 plus A2 minus gives Ha2 plus A1 minus. So now we add it up. That's what I just did. So what is the K? Is K times K. Ka1 times 1 over Ka2 is Ka1 divided by Ka2. And with this was the right answer. Okay? So it's very simple, this stuff. All you need to do, turn it around and multiply it with -1, and then make sure that you look at the Ka appropriately. So, you know that salts, they have ions. And if you have a salt solution, for example, cooking salt, sodium chloride, if you throw this in water, it completely dissociates into sodium ions. These are positive ions, and chloride ions, these are negative ions, so cations and anions. And they can conduct electricity. They can carry electricity, these ions. So if you have water, for example, water, you have a lot of H3O plus and OH minus in water. How much do you have? 10 to the minus 14 is the product. So you have 10 to the minus 7 molar OH minus and 10 to the minus 7 molar H3O plus. That's not a whole lot, isn't it? So why don't I give you a couple of questions here? And I want to do the following. Let's see, I go down here for a second. If I could have the screen here, please. Not the screen, the demo. Thank you. All right, so you see we have solution 1 is HCl. That's this one here. Solution 2 is acetic acid. That's this one. As indicated there, it's both red. The solution 3 is water. Solution 4 is NH3 plus water, okay? And solution 5 is sodium hydroxide dissolved in water. So this has a pH of 1, 4, about 7, 10, and 13. So I have a lamp here. You see that lamp? This is interrupted. The circuit is interrupted. See these two prongs there? This is 110 volts is on there, okay? Don't do this at home, please. It's 110 volts, and I hope that Karen comes, that I don't electrocute myself. No, just kidding, okay? And so if I put this in water, you think that this would conduct electricity, that that bulb goes on? What do you think? Dim, you think, dim, okay? I don't know, it must be on, okay? So now if I put this in solution number 1, that's the HCl. What do you think the bulb will be doing? Huh? Oh, there you go, lights up. Why? Because you have HCl is completely dissociated in H3O plus and Cl minus. And H3O plus is a high concentration, 0.1 molar, or we have, 0.1 was pH 1, 0.1 molar, and Cl minus conducts, is an electrolyte, conducts electricity very well. Now the next one would be acetic acid. Is this a bright bulb? So we have established this here already. This was bright, and now what this one? Would it be dim or dark? Why would that be? Okay, it's not so many of them there. Okay, there are some of them of AC minus and H3O plus, but compared to HCl, it's not completely dissociated. Actually, the equilibrium is very much on the left side. All right. So water we have seen already is, so this was dim here, and water doesn't conduct at all, or not very well, let's put it that way, okay? So what do you think what happens in sodium hydroxide? Will it be bright or dim? It will be bright. Anybody, any takers? Bright, okay. Oh yeah, it's bright, of course. The sodium is a strong base. It completely dissociates in Na plus and OH minus. So it carries the electricity very well. Now the ammonia is obviously a weak base. So what will be the brightness of the bulb? Dim. And that's correct, because the equilibrium is very much on the left side. The ammonia has not dissociated very well. There's only a little bit of NH4 plus and OH minus, and that's, you see, it carries the electricity, but not enough there to give you the full current, okay? So now we're going to do this here, and Karen will help me. So what we're going to do is, so this is what happened here, and this is what happened here. I leave you that here. So we mix now solutions 1 and 5. 1 is the HCl and the sodium hydroxide. And I ask you the first question, will it be acidic, neutral, or basic? That's the first question. Why don't you give me your answer, please? Acidic, neutral, or basic? So I mix HCl, pH 1, with sodium hydroxide, pH 13, and I want to know what happens to the pH. Pardon? Yeah, they are the same molarity. Yeah. Because 13 and 1 must be the same molarity. 0.1 each. Take your time, take your time. We are not doing it yet. If you have sodium hydroxide and HCl, and you pour them together, so what happens? Isn't it like a titration? Okay. Why is the what? Lona Ida, this is the second part of the question. Okay. No. Just look at the pH at the first row. The second row is the next question. So will it be acidic, neutral, or basic? See, you got this. Of course, it will be neutral. So that means pH 7. You have the same amount of H3O plus here as you have the same amount of OH minus here, and they completely neutralize each other to pH 7 till they have water. You have water, so that's pH of 7. So now comes the kicker. Is when I do this and put the bulb in there, is it bright, dim, or dark? Why don't you answer that one? So we neutralized it, and I want to know if it's bright, is A, B dim, and C is dark.
Answering the wrong question.
I did say it, though. So we are now at the second part of the question, the bulb question. Does it conduct electricity very well, not so well, or not at all? So what is it? Let's see, what do you think? Okay. So you have sodium hydroxide and HCl. So the OH is neutralized by the H3O plus molecule by molecule. And since they are both the same concentration, so that's neutral. But what do we have left over? There was the sodium from the sodium hydroxide and the chloride from the HCl. You think it went up in the air, or where did it go? It's still in there, isn't it? So why don't you think about this? If it conducts electricity or it doesn't conduct electricity, or it conducts electricity a little bit, and I give you 1 minute. You can discuss it with each other. Please. Think about it. So what is it? Henry?
Because like this.
No. Yes.
Why is it not true? All the hydrogen ion and hydroxyl ion combine to form one.
And what else is in the solution? I said it before. Okay, let's have a look at this. It shifted a little bit, huh? All righty, so why don't we do that then? Let's see, have a look at this. So if you could have the camera up there, please. Wait. We need to see everything. Wait. Not that they... So Karen will take solution 1 and 5, sodium hydroxide and HCl, and we will mix them. And they have an indicator in there which is sort of yellow when it's neutral. So you said the majority says that it will be conducting electricity, but quite a few people say that it is not conducting electricity at all, and some are a little bit, okay? So why don't we do that here? Oh my! Of course! What happened? You have sodium hydroxide and HCl.